Good morning. We are going to continue on with our discussion of different data structures today, or actually not really. We're going to talk about two ADTs today, stack and the queue, and how you can implement them with different data structures. These two data structures are really similar. They're both sequences of homogeneous data. Whoa. Less fancy, it means you're storing many objects of the same type. We're probably going to talk about stacks and queues containing integers for the most part, but they can theoretically contain any data type, even object types, even other data structures. So with stacks and queues, what makes them important and what makes them different from each other are the order in which items are added and removed. In a stack, it says here, new data can only be added at the top and old data can only be removed from the top. I like to think about it not vertically as in top and bottom, but linearly as in left to right in a list, because that's how you'll end up implementing them. So in a stack, only the last item that you most recently inserted, like the rightmost item in a left to right list, only that one can be removed. So we have an acronym for that, LIFO, last in, first out. And I guess you could actually ignore this stuff I said about thinking about this horizontally, like left to right. Actually think about it in terms of first to last item. But anyway, good metaphor for a stack is a stack of books. So if you have a few, you could only put new books at the top of the stack and take new books from the top of the stack. Elements on the stack that aren't on top are inaccessible. Can't get to them. A queue, on the other hand, is better modeled as a lineup, like at a store. I don't have as compelling a physical metaphor for this, but you can bear with me as I attempt to hold these books upright. If you already have a few items in your queue, new items join at the back of it, and items are removed from the front. Like the slide says, think of a line for purchases at a grocery store. New customers join at the back of the line, and the next customer to be served is the one at the front of the line. And that's today's ADTs in a nutshell, really. They're basically lists, but with a dynamic size, so like the number of items in it can change, and some pretty strict restrictions on which items you can remove or even access. So you might be thinking, like, what's the point? Why not just use lists for everything? I'd rather be able to remove or access any item from the list. Well, stacks and queues may not be immediately useful looking without any context, but it turns out there are many algorithms that benefit from having a collection of data where you can only remove from the top of the stack or the front of the queue. So with that in mind, having a data structure that can only do those things, that makes taking from the middle impossible, prevents a lot of different bugs. It's like what we were talking about with those linked list variations, making null checks unnecessary, like making it impossible for it to crash. Stacks and queues follow a similar idea. They're restricted, But when you actually want those restrictions, it's useful to rule out them doing anything else. So we're back to looking at ADTs as a list of operations, and we're going to look at data structures to implement them later. Before I go over the list of operations, I wanted to share a perspective on ADTs and data structures that I found that might be useful for understanding. This is lifted from the Wikipedia article. ADTs are from the perspective of the user, so they detail what you could actually do with the thing, while data structures are from the perspective of the implementer, so how it works. So when you're making code for storing stuff and operating on it, you're working on data structures. When you're making code that uses someone else's data structures, you're thinking about ADTs. Cool. So what is a stack from the perspective of a user? List of operations, obviously. Push adds a new entry to the top of the stack. Pop removes the top entry from the stack and returns it. I'm now able to read this data. Top returns the top entry, but doesn't remove it from the stack. In some algorithms, examples of which you'll see later, it's sometimes useful to just check what the most recently added item is while still keeping it in the data structure. Is empty checks if the stack is empty and returns a Boolean. This is currently not empty. And the constructor creates a new empty stack. There's also another operation, isFull, which throws a little tiny wrench into the distinction between ADTs and data structures, because the presence of this isFull operation will actually depend on the implementation choices made in the data structure. Basically, isFull checks whether the maximum capacity of the stack has been reached and prevents you from pushing any items to the top if it has. This is only relevant if you're implementing a stack using an array, because arrays have a fixed size. If you're implementing a stack using a linked list, then you'll only run out of space for your stack when you run out of memory on your computer, and at that point you have much bigger problems. So isFull is usually only present on a stack that's implemented using an array. I guess to reconcile that with our intended separation of ADTs and data structures, we can say that isFull is always present in the stack ADT. It's always going to be a method, public method in the stack class, no matter how that stack class works. But we could say that on a linked list based stack, isFull just always returns false. The behavior will be slightly different based on implementation choices. It's kind of a shame that this is the thing. It kind of ruins the clean mathematical sort of model that ADTs work the same way, externally, no matter how they were implemented internally. But whatever, our models aren't perfect. We have some notation for a stack. You don't have to memorize this, but you should be able to recognize this. The left bracket represents the bottom of the stack, and that right angle bracket is the top of the stack. So you could imagine the stack growing in the direction of that arrow defined by the angle bracket. So I've just drawn the numbers stacked in an arrangement that would be more intuitive and will hopefully help you understand the stack notation. 12 is at the top, so it was the value that was most recently added to the stack. And if you called pop, it would remove and return 12. This example, additionally, is super important. I can guarantee that the quiz tomorrow will have something that looks like this, except like those two columns will be blank. Except for the first column showing an empty stack to remind you of the notation. So you should definitely prepare for the quiz by going through this example, like basically recreating the return and stack columns on a separate piece of paper, and then check your work against this afterwards. Thinking about whether there's anything in the example that I should go over, but it should be straightforward. Like, we push 8, so there's now an 8 at the stack. Push 20, so there's now a 20 that is above that 8. Top doesn't modify the stack, but it returns the topmost element, 20. Pop also returns the topmost element and removes that element. Is empty is false because there is a value in the stack. Pop returns the topmost item and removes it. And at that point, is empty is true because the stack is empty. It's a straightforward set of operations, but once you're using a stack to implement some algorithm that can use it, it can get pretty mind-bending. Oh yeah, speaking of algorithms that could use it, here's something that basically every modern code editor does. It's called bracket matching. You have strings like these ones. In this case, they represent sequences of arithmetic operations, but you see these brackets all the time in code as well. So a program with several lines of code would be relevant for this example as well. So you're given that, and in order for the arithmetic expression to make sense, to be well defined, and in order for your code to compile, all of the brackets need to match. For every opening parenthesis, there needs to be a corresponding closed parenthesis. For every opening curly bracket, there needs to be a closing curly bracket, and same thing for square brackets. One of these lines is bad. The brackets aren't correctly nested. There's either a opening bracket that doesn't have a closing bracket or a closing bracket that doesn't have an opening bracket. But it's probably really hard to tell which one is bad. I don't even know which one is bad. So, given its importance for math and especially compiling programs, it makes sense to want an algorithm that matches brackets. And it turns out a stack is really useful for this. You basically have to go through the string character by character and then add all of the left brackets you see onto the stack. And then, when you encounter a right bracket, I'm going to go through this kind of slowly. Try to think of what you might do to the stack when you encounter a right bracket as I'm waffling. Talking slowly. When you encounter a right bracket, you should remove it from the stack. And then, since you're adding to the stack when you see a left bracket and removing from the stack when you're seeing a right bracket, those actions canceling each other out mean that once you've finished processing the string, you'll be able to tell if the string is bracket matched correctly by checking whether the stack is empty. So this is a potential implementation of the algorithm. The details of bracket matching aren't very important. Like, this is purely in service of giving an example of why stacks are useful. And for this course, you need to learn about stacks. This course is not about bracket matching. But I'll still spend a little bit more time on this example. We see this is the part where you add a opening bracket to the stack. And then this is where you remove a closing bracket from the stack. Note that there's another check that I didn't really mention in my earlier explanation. You also want to check if the top bracket in the stack matches the one that, you want to make sure that the top bracket in the stack matches the closing bracket that you just found. Otherwise, it would be unbalanced, unmatched. And then you check if the stack is empty at the end. So even though this particular algorithm, this particular application isn't important, still might be a useful study tool. If you're not certain that you understand how stacks and their operations work, do some bracket matching. Write out an arithmetic operation where you know that each opening bracket has a corresponding closing bracket. Write an arithmetic operation where you know that the order of brackets is messed up, and then go through this algorithm and see if you get the correct result. Bracket matching is not important for this course, but stacks are. I'm going to do a quick run through of that algorithm with this string, and then I'm going to stop talking about bracket matching. So we have our stack. Initially it's empty, and you probably would want to draw it like this, but I don't feel like erasing and redrawing the angle bracket a million times. So I'm just going to put it here, give myself a ton of space. And then let's go through the string character by character, pushing any opening bracket we see. So that's a number, we ignore it. That's an operation, we ignore it. That's a bracket. So we just pushed that curly bracket onto the top of the stack. Ignore, ignore. Ooh. That's a bracket, so we add it. We push it more specifically. Number, ignore, operation, ignore, number, ignore. Closing bracket. So we just found a closing parenthesis. So we check the top of the stack that returns the top stack or top of the stack without removing it. We see that the top of the stack is a left parenthesis that matches the right parenthesis. So we're good. We pop it to remove it from the stack, and we continue. I'm not going to keep checking all the operations and numbers. The next bracket that we find is an opening square bracket, so we push it, and immediately after that, an opening parenthesis. Then we find closing parenthesis, a closing square bracket, and a closing curly bracket in that order. And so for each one, we would check the top of the stack, verify that it matches the closing bracket we're seeing, and then pop it. At this point, we've reached the end of the string. We check that the stack is empty, and we're done. If you had a string that wasn't bracket matched, something like that, then as you're going through it, you would push this left bracket or left parenthesis, opening parenthesis, whatever, onto the stack. You would reach the end of the string, see that the stack is not empty, and your algorithm would return false or not bracket matched. Cool. There are two main ways we're going to cover to implement stacks and also queues once we go into more detail with them. You would use either an array or a linked list. In a future assignment in the course, I think assignment 4, you'll need to implement a stack and a queue for the sake of executing some more complicated algorithm that requires a stack and a queue. And you're going to have the choice of whether to use an array or a linked list. And you'll be expected to justify your choice with why the data structure you chose leads to a more effective implementation of the ADT. Unfortunately, this exercise isn't that good of an approximation of the implementation decisions that I've been talking about that you would find in real practical applications. When you're considering a linked list versus an array for a stack and a queue, one of those two data structures is just going to do a much better job than the other. This is the rare case when one solution is actually just better. Incredible. I'm going to cover both the array and linked list implementations of stacks and queues. And as you're listening, try to figure out which one's better. You're working on assignment 4 in advance that way. My shoe keeps coming untied. Why does that happen? I'm not even walking. I'm going to leave this as an exercise to the reader. Math code word for I don't feel like doing this. Think about how you would implement the stack ADT using an array. Spoiler alert, it's going to look kind of reminiscent of this notation. You're just going to have an array where the bottom of the stack is the low indices, like starting at 0, and the top of the stack is the high indices. And then all of the functions will be relatively simple to implement. In the in the assignment where these come up, making a stack and a queue is not going to be the hard part. Anyway, the last bit of this exercise is to think about the time complexity of each of the functions. I'm not going to spoil this right now, but I'm probably going to end up mentioning it anyway in further discussion of this data structure. As usual, try to beat me to it. Try to think about it while I'm talking and predict what I'm going to say about the big O notation. For that part, if you want to, you can analyze the code you write, make a cost function with summations and stuff, and then prove that it is in a specific big O group by the definitions. You can do that. That would probably be decent studying for when cost functions and big O notation come up eventually again on probably not future assignments, but definitely the final exam. But if you don't want to do that, you probably don't want to do that. I know I don't want to do that. You could get your first bit of practice using big O notation in the way that it tends to actually be used in the real world, which is to say, eyeball the function, look for things that are generally signs of different big O groups. Like if it has two nested loops, it's probably O of n squared. And then use that to, as quickly as possible, make a guess at what the time complexity is. And then maybe use the definition to verify your answer. There's going to be pseudocode for the linked list version of this data structure later in the lecture, so I'm going to demonstrate that type of quicker, less formal analysis when that comes up. But speaking of the linked list implementation, we have some decisions to make when implementing a stack with a linked list. With an array, there's only one type of array, so you just use that. But with a linked list, you have to go through all of the stuff that we talked about last class. Are you going to sort it? Are you going to use dummy nodes? Is it going to be circular? Is it going to be doubly linked? Well, the question of sorted or unsorted is irrelevant. It's a stack. It should be sorted by the order of the things you stacked on them. It should be sorted by the order in which you put them on the stack. So you could forget about this. But then the other three, I don't know. They might be useful. But as you hopefully already read on the slide, our extensions of the basic linked list were motivated by things like searching or iterating that don't really apply for a stack. You're never going to search a stack for a specific item because that's not what a stack is supposed to do. If you need searches, use a more complicated ADT. So there's no searching or iterating, which kind of makes the doubly linked list extension irrelevant, as well as the circular one. And you know that, oh wait, I'm going to cross it. Those aren't relevant because you're never going to be iterating through the list or searching it. The last bit is that since you're only ever going to push and pop from the top of the stack, you're only going to be adding and removing linked list nodes from specific locations, or honestly just one specific location of the linked list, which makes the whole thing a lot less error prone and makes nodes kind of unnecessary. So that makes the implementation of a stack using a linked list pretty easy. You could write them if you want. They're also on the next slide. And they're all going to involve adding and removing nodes from the top, basically. So, say I have a stack implemented using a linked list. And then I add something to it. I push something to it. In the theoretical representation, you just draw the number. Your code's going to be slightly more complicated. Wait. Yeah, I'm going to keep that null there because we're going to make a new node that contains the data we're pushing and a pointer to the top, which starts out as null, and then reassign top to point at that. I'm going to pop another node onto, pop another value, push another value onto our linked list for demonstration. Oh, wait. Oh yeah, sorry. Each new node in this implementation replaces the top. A bit tricky. So why did I put the 2 before the 8 when it may have been your intuition, and it was clearly my intuition, to place a new node at the end of the list? Well, that's because of how element access in a linked list works. If I put the new top value in a node at the end of the list, then popping it, or even just accessing the top, would involve iterating through the entire list to get to it. This would have time complexity O of n because it takes roughly one operation per item in the stack. A huge waste of time when you could add the elements in the linked list in reverse, and then when it comes time to view the top item or pop the top item, it's already pointed to by a variable named top. It's easy. So that sort of smart implementation lets us pop items and also view the top in O of 1 constant time. It's constant time because it takes the same amount of time no matter how many things are in the stack. So anyway, if we're popping, in the mathematical form, you just erase the number and you're done. But then in the code, you take the data of the first node in the list and make that the return value. And then reassign top to point at the thing that top was pointing at. And now the node with 2 in it doesn't have anything pointing to it, so eventually Java's garbage collector will destroy it. The first node in the linked list is now the one containing 8. And then we return top data. Yeah, I'm going to leave it like this for the annotated slides. The top method is really easy. You just access this and return it. Cool. I hope that you really internalize the idea of implementation decisions affecting time complexity. It would be, as I mentioned before, a huge waste of time if we organize a linked list in a more intuitive order and that caused us to have to traverse the entire list to access the top element. By putting them in reverse, we managed to make it so that works in constant time. And I guess that's the spoiler that I mentioned earlier. All of these operations are in O of 1. Oh, and of course, is empty. That just checks if top equals null, because that in a linked list means that there's nothing in the linked list. Linked lists on their own have no size constraints. Memory is allocated as needed, and like I said earlier, if you run out of memory for your linked list, that means you've run out of memory for your entire computer. But you might want to set a maximum size anyway in order to make the linked list-based stack work the same way as an array-based stack. So if you wanted to do that, you would add a constant max size and a variable, what did it call it? Stack size? Yeah. So we'd have something like this and something like this. And this would be used to keep track of the stack size throughout the execution. So push would increment that. Pop would decrement that. And most importantly, the push operation would refuse to work if the stack size is already at its maximum. So here I'm using the comparison if stack size is strictly less than max size. And then if this if condition is false, if stack size is equal to or somehow greater than max size, really shouldn't be greater than, it's sort of up to you to decide what to do. This implementation, like this pseudocode, is fine. The push operation can just do nothing, but it would be helpful to communicate somehow that the operation failed. So what I would do personally is replace or add the return type bool, and then, oh geez, this is gonna look terrible. Wish I could add new space on this pseudocode. Whatever. Return true if the item that you intended to push did actually get pushed, and false if it didn't. Yeah, this is comprehensible enough, I think. Sure. And then the isFull method would just compare stack size to max size. This syntax is kind of neat. For readability, it's perfectly okay to expand it into something like, if stack size equals max size, return true, else return false. But stack size equals max size is a Boolean expression. It will resolve to the value true or false. So this is cool too. So that's it for stacks. The queue works very similarly, but has a few like gotchas that make it a bit more complicated. Of course, it makes the data structures that you use to implement it more complicated. The ADT is still basically as simple as a stack. Ugh. So, actually, I don't want to balance all these books. I'm just going to draw stick people on the slide to illustrate a line of people, like lining up for something. So, we're going to model items in the queue as stick people in a line. The line is going this way. So, the best I could do to provide an equivalent to the stack of books representing a stack. In queue adds a new entry to the back of the queue. New person joins the line. DQ removes the entry from the front of the queue and returns it. Someone else is now at the front of the line. Front returns the entry at the front of the queue, but doesn't remove it from the queue. Is empty checks if the queue is empty. Dang, I totally remembered noticing that mistake last term, and I was like, oh, I should correct that for next term. Maybe next term. The constructor creates a new and empty queue, and isFull can be used if there's a size limit. Whether it's actually enforced by your implementation if you're using an array, or just made up if you're using a linked list. I guess you can also have a size limit that isn't imposed due to technical limitations, but still exists for the sake of business requirements. Like maybe a new hybrid gaming console system is coming out on June 5th, and there are pre-orders that are a total mess and have you wait in a queue online before you could go to the website and pre-order it. That would be a queue with a size limit, not due to technical restrictions, but due to real-world constraints on the application being programmed. Everything about the stack everything about a queue is similar but different from a stack, including the notation. We use two left angle brackets to write out queues. And those angle brackets point from the back of the queue to the front. In my example above, it probably actually would have been more helpful if I drew the arrow going this way. Now, this person is at the front of the queue, and this person is at the back. The person who is basically at the front is probably pretty mad right now. Neither direction is like objectively correct. It's not like there's a canonical direction that all queues must face for very good reasons. But this is just the convention that we happen to go with. We want to be consistent, so we're going to write queues as going from right to left all the time. So if we add a new entry, it appears on the right side of the queue, the back of the queue, and entries to be dequeued disappear from the left side, the front of the queue. Just like the stack syntax or stack notation, you don't need to memorize like what this is supposed to look like. I mix it up frequently myself, but you should be able to recognize it when you see it. And on the next quiz, there will almost certainly be a question like this, where the first line is q equals new q, and then you have an empty q right here to remind you of the syntax. And then you have to go through all these operations and list the return values and write up or draw the queue in its current state. Yeah?
So those for next quiz, is that in reference to the quiz tomorrow?
Yeah, tomorrow. We're going to go over the linked list implementation first. This is going to be more complicated than the stack, no matter how you slice it. We're going to use a linked list with 2 pointers, one to the start of the list and one to the end, because with just the way that a queue works, we're going to have to add elements to one side and remove elements from the opposite side. This is more complicated than a stack where you add and remove elements from the same side. So you have a linked list. This head is basically the same as top as seen earlier. Actually, I'm going to erase that to prevent confusion with the top of a stack, which I'm not referencing. I'm referencing the top of a linked list. To avoid such confusion, we're calling it head instead now. So there's a head and a tail. Which one should be the front of the queue and which one should be the back of the queue? Well, I don't know. Let's look over these and try to figure out, like before we write even a letter of code, which one would be better for which side of the queue. So at the head, you can add elements easily. You just make a new node, make it point to head, and then reassign head to point to it. So that's simple. Means that the head would do well as the back of the queue where elements are inserted. So that might make you want to make the tail the front of the queue where elements are removed. Well, problem is It's super inefficient and bad, and I deliberately got it wrong so I could demonstrate why it's wrong. If you want to delete the last element of a linked list, there's nothing you could really do. You could maybe, I guess, set tail to null. But that wouldn't do anything useful because we all know that this node should be the tail. Plus, it still points to that last node. You've done nothing but just break the data structure. To delete the last element, you have to somehow access the second last element so that you can reassign its link to null. But starting from the tail pointer, we only have access to this. There's no arrow that points to the second last node. So you would have no choice but to iterate through the entire list until you reach the end, keep track of the previous node along the way, and then backtrack to the previous node once you've found the last one in order to get the second last. You should hopefully be getting this sort of intuition by now. This would involve going through all of the items in the list, so it would take O of n time. Huge contrast to how adding items at the head just involved doing a constant amount of operations that didn't depend on the number of items in the node, and number of items in the list, and thus took O of 1 time. So I guess you could fix this problem by making the list doubly linked. That way, you use the tail to get to the last element, use the prev pointer to access the second last element, and then you can do your thing. And that's totally valid. If you do that on an assignment, the marker will be like, cool, that sure is a doubly linked list. But you can be a bit smarter about this. There is a way to get constant time enqueuing and dequeuing with a singly linked list. You may notice that inserting at the end of a linked list is easy. We have access to the last item, soon to be second last. So you make a new node, make the node pointed to by tail, point to it, and then reassign tail to also point to that node. So it's added to the end of the list. Of course, a linked list where we can just add to both sides isn't very useful. Hopefully there's a good way to delete elements at the start of a linked list, and there is. You just reassign head to point to the same node that the head's link is pointing to. And that's it. Java's garbage collector will eventually notice that nothing points to this and destroy it. Cool. So it turns out, at the head of a linked list, both adding and deleting a node are easy. Both are able to be done in constant time. But at the tail of the linked list, it's easy to add a node, but not easy to delete a node. Remember that none of these operations acted any differently based on the length of the list, except for deleting a node at the end. at the tail. Because of this, the convention is to use the front or the head of the tail as the front of the queue, and head of the linked list as the front of the queue, and the tail of the linked list as the back of the queue. You could also use a circular linked list. Similar to the doubly linked list case, if you do this, the marker will go like, circular linked list, cool. And then give you full marks because they have better things to deduct marks for. So with a circular linked list, you would only have one pointer, and it would be the tail of the linked list. So even though the circular nature of this kind of removes any notion of front or back, we consider this the head of the linked list, and this the tail, and thus the back of the queue. So I don't think I'll go into much detail on this because there aren't any problems to solve for this. It just turns out this works. This is another potential way you could structure your data. Amazing. And it lets you do both the in-queue and DQ operations in constant time. So, implementing a queue with a linked list is doable. It's a little annoying, but it's doable. Turns out implementing a queue using an array just sucks. It's real bad. This exercise to the reader is purely optional. It is arguably good for your learning and education to torture your stuff on trivial things like this, but you probably have better things to focus on in this course. I'm going to talk about it hopefully enough to emphasize how cumbersome it is, but no more than that. So suppose we had an array. Woo. Each of the squares in the little rectangle I'm making is an array index. Which side of the array is the front of the queue? Which side is the back? I don't know yet, but I'm going to make it so, just like as a start, as a first guess, I'm going to make it so the back of the queue is the high indices, because it makes it so as I in-queue items, I could just access progressively higher indices. Pretty easy. So I just in-queued 1, then 2, then 3, then 4. What am I going to do when I dequeue an item? Well, I'm going to remove it from the array for sure. Replace that number with a value that is obviously a placeholder, like -1 if I'm only counting positive integers, or null if I'm storing objects. And then, now what? I guess that I could shift every element over 1. But look at how much time this is taking. O of n in this economy? No. We already got O of 1 in queuing and dequeuing using a linked list, so we should try harder to not make linear time operations for our array-based queue. So we're stuck with indices here. You enqueue some more items, you dequeue some more items, and it becomes clear that you have to keep track of the index of the front of the queue. And probably the back too. So that you know which array index you need to look in when you do the dequeue or front operation. And you know what array index to insert into when you do the enqueue operation. Oh no, I guess I've ran out of space. Sucks, I guess. Gonna dequeue a few more items. And now I have just one item in the queue, front and back are at the same location. Dequeue that, and I guess my queue is just broken. I can reset after this, like maybe start inserting items at the natural front again. But that still leaves a really crappy situation where you have the back of the queue towards the end of the array and you have no room left to enqueue any items. So we should solve this. Turns out a nice way to manage this is to make the indices wrap around. So I want to insert or enqueue an 8 into the back of the queue. The back is here now. And then if I, actually I'm not going to demonstrate dequeuing because like, even though that F for front pointer would eventually wrap around, that would make it so the front index would be less than back index again and make the picture look comprehensible again. And I want to keep emphasizing that it can get weird. So we're in a situation like this. The queue just occupies a region of the array that wraps around at some point. You would use the modulo operation to accomplish this. It would be something like b equals b plus 1 modulo array size. I'm just going to write size. So that operation would be what you do when you enqueue an item and increase the value of b. Like I'm doing right here without any wraparound. And that's basically how you would implement a queue. I guess there's even more reasons why this is annoying. We already answered this question. We would have to keep track of 2 indices, front and back. If there's no more room at the end of the array, but there is room at the beginning of the array, you would wrap around using modulo. But then I'm not even gonna bother with these 2. The answer to both is some variation of check if b equals f. Oh wait, actually I just figured it out in my head. You would probably want to keep track of the number of items in the queue instead of comparing indices at all. And then it would be full if the number of items equals that predefined capacity. And then it would be empty if b equals f. and the number of items doesn't equal the capacity. Ah. So yeah, array-based queues, don't do it. So there's about 10 minutes left, and another example of an application of stacks. Because it turns out stacks are really useful for solving arithmetic operations. You type this into some online calculator or something, and it probably uses a stack to process what operations to do and in what order. But just like bracket matching, this isn't really important. This is not a arithmetic operation solving course. It's a data structure course. So I'm making this optional. I want to get a little ahead on the content just to make sure that we're still on schedule after the quiz eats a huge chunk out of tomorrow's class. I was thinking of what to exclude, and this is easily the least important but largest topic that we cover around this part of the course. I might get to it if there's time we need to fill at some other point, but nah. Instead, we're going to do an intro to an intro of the next major topic of the course. And for those of you who have taken earlier comp sci courses, I don't know the exact curriculum, but I think that stacks and queues are covered to some extent. You might have learned a bit about stacks and queues today, but this is the first topic that will probably be new the first programming related topic that will most likely be new for everyone. We're going to talk about the data structure for tables called the hash table. We'll go over why hash tables are interesting, but we have to sort of motivate it with a review of the table data structure. So remember that a table consists of a bunch of entries, where each entry consists of a key that uniquely identifies the entry and other attributes associated with it. A common example for this that I'm going to keep using is some sort of software to keep track of students at a university. The key would be student number to uniquely identify the student, and other data would be everything else: their name, year, program, grades, GPA, that sort of stuff. And you can imagine tracking a lot of other types of data with this too. Could be mapping like days to events in a calendar or something like that. The table is sometimes called a dictionary, and to that effect, I want to mention in Python, the dictionary type, that's a table. You map keys to values. That is an implementation of the table ADT. And also, last time I checked, because this can't change across Python versions, the Python dictionary uses the hash table that we're about to study. So anyway, other things we need to clear up before continuing is that each key is unique. No duplicates are allowed. No two students can have the same student number. And that applies for any collection of data that you would want to store. And the entries are not in any particular order. Search by key rather than position. And in effect, this makes it so the table ADT doesn't have any operations for iterating through it. I believe also in Python, it's kind of clunky to loop through all the entries in a dictionary, and Python's documentation takes care to mention that it doesn't guarantee any specific order for the things inside of the dictionary. This property of tables is mostly for technical reasons. Unlike stacks and queues, which have limitations that are sort of for the sake of focus, because it makes it less error prone if you make a data structure that only supports specific operations when those are the ones you know you're going to use. Rather, the lack of ordering in a table is to accommodate limitations of the data structures we use to implement them. This will make more sense as we grow to understand hash tables. I think in the rest of the class, I'll keep talking about the table ADT, but we'll draw the line at data structures. We're only going to talk about theory in the remainder of this lecture. So, insert dk adds an entry d with key k to the table. So if you were inserting or enrolling a student in a class with this sort of ADT, the entry would be the student and their information, their name, their year, their program, and k would be the key student number. Depending on the technical details of the implementation, the insert method could also just take that data, and the key would be some specific attribute of that data. So in this case, you would call insert with a parameter for a student. The student class would contain a variable for its student number, and the implementation of the table would just know that the key is supposed to be the student number. Delete takes a key, looks up the entry with that key, removes it from the table. Search, also called retrieve, finds the entry with key k. Search and retrieve actually do slightly different things. Search just tells you whether an entry exists with key k, and retrieve actually returns that data. The constructor is empty, is full, work exactly as you'd expect, and there's an optional print operation that prints all entries in the table. Is it 12 o'clock yet? We got 15 more seconds. Yeah, stuff to think about. This aside I won't really cover, but it's useful to read for real-world applications. Woo, it's noon. Get out of here.